In this video, we're going to learn how to first build and then differentiate a computational graph. Now, a computational graph is a way to graphically represent a set of complex mathematical expressions in terms of their individual operations. This is how programs actually break down complex expressions and then evaluate them and forms the basis of automatic differentiation systems. So let's start with a simple set of expressions. We have z is wx plus b, where this dot indicates multiplication. And we have f is e to the power of z. The two simple expressions. The first thing we need to do is break this down into their elementary operations. So let's introduce an intermediate variable, a, which is going to be equal to w times x. Now we have z, which was wx plus b, so now it's a plus b. And finally, we have f, which is equal to the exponential of z. So now we have three simple expressions, one operation each. And now we'll start building the graph. So let's say w and x. We're going to give them values so that you actually see how to evaluate this graph as we build it. And the process of evaluating the graph to get the output is called a forward pass. Now, typically you'd build the graph and then evaluate it for the values. We're going to do that together. So the first node is w times x, right? Which we represented there as w dot x. So that is 0.2 plus times 1 in this case, which is 0.2. And that gives us the value a, which is our intermediate variable. Now, the next node was a plus b. We know a is 0.2, b is 0.3, where I've used the yellow to indicate the actual variables or inputs coming in, and the pink denotes intermediate variables, right? So we have a plus b, and the output was z. In this case, 0.3 plus 0.2, which is 0.5. And then the last node in this expression, which was the exponential of z, and f is what you get. As a result of that, the value of the exponential of 0.5 is 1.648. And there you have it. You've built your computational graph. You've got the inputs coming in. You've got the nodes that break this expression down into simple operations. And you've got the output f. And we've actually, while building it, also passed these values through them to get the output for this set of inputs, 0.2, 1, and 0.3. And this process of getting the outputs once the graph is built is called the forward pass. Now, the next piece of this puzzle is, can we compute the sensitivity of the output of this computational graph with respect to its inputs? So in this case, the derivative of f with respect to w, x, and b. And this is kind of how an automatic differentiation in an Autograd system is set up, right? It's designed that once you do your forward pass for those set of values, you're trying to find the sensitivity of the output with respect to the inputs. So let's look at a simple example first, and we'll see how, using the chain rule, we can achieve this. So let's take a simple example. We're taking a snippet, let's say, from a complex graph. Let's say we're taking that one node out in the middle of a graph, right? And it's not the graph we've looked at. It's just assume this is a middle node of a graph. So it's taking an input x, the node is multiplying it by 2, and you get the output y, right? And I've given it values. Now, we assume that now this value is passed forward and some expression is evaluated. Now, to compute the sensitivity, we do what is called the backward pass. So from the node ahead, the sensitivity, we say f is the output of this entire graph. We say we are passed back the sensitivity of f with respect to this value y. Now, what we have is dou f by dou y, which has been passed back. We're going to call that the upstream gradient. What we have here for this node is its local function. So you can compute the derivative of this function with respect to its input. The output or the function is y. So we're going to say we want to compute dou y with respect to dou x. That's called the local gradient. In this case, it's quite simple. It's just 2, right? And then what we want is the sensitivity of the output, which is f with respect to x in this case. And so dou f, dou x can be given by chaining the upstream gradient dou f dou y with the local gradient dou y dou x, right? So dou f dou x is dou f dou y times dou y dou x. And then what we can do once we compute that, given this is a node in the middle of this graph, we can now push this further down. And what we get then is what we call the downstream gradient. So dou f dou x is the downstream gradient. It's the gradient of the objective or the output of this graph with respect to the variable x here. And this can now be passed further down, right? So that the next node can now use this to compute its sensitivity. Hopefully this is clear. Let's now do this for the graph we've looked at, right? So we'll start with the last node. And as the name suggests, the backward pass means you'd start with the last node and move all the way back to the first one. Now, this is the last node. So the upstream gradient, there isn't one, right? It's the last one. So we're just going to say dou f with respect to f is 1, right? The derivative with respect to itself. Now, what's the local gradient? It's dou f with respect to dou z, right? So dou f by dou z is dou by dou z of e to the power of z, which is e to the power of z. And e to the power of z we know is 1.648. So that's that. So we've got this value. We have nothing to chain it with. You can technically chain it with dou f, but that's 1. And so what's pushed back is dou f, dou z, which is the derivative of the output of the graph with respect to this intermediate variable z. And we have the value 1.648. Now let's move to the middle node, the second node. We've got this upstream gradient, which has been pushed back from the node ahead. We now need to compute the local variables of the local gradient. So the derivative of z, which is a plus b with respect to b, is 1. We know that. And the derivative of the same expression with respect to a is 1 as well, right? There's no dependence on b here when you're saying the derivative of a. Dou a by dou a is 1. And now we can compute the upstream gradients. Now, the downstream gradient, sorry. So let's take the first one, b. That's an input. So dou f dou b is using the chain rule, dou f dou z, which is passed up, from upstream, times dou z dou b, which is the local gradient, which is 1.648 times 1 is 1.648. And that's the end of that. That's the input. So in this direction, we don't have to push further downstream. On the other hand, a is an intermediate variable. So we'll use the same approach. Dou f dou a is dou f dou z times dou z dou a. Use the chain rule. It's 1.648 times 1 is 1.648. And that now is pushed to the first node, right? So it's pushed further down. And so now moving to node 1, we know dou f dou a now, which has been pushed to us, is 1.648. You want the local gradients. So dou a with respect to w, dou a dou w is the derivative of this with respect to w. It's a multiplication, and w and x are independent. So dou f, dou a dou w is x. In our case, x is 1. So dou a dou w is 1. And dou a dou x is w. In our case, w is 0.2. So dou a dou x is 0.2. And now we can compute the derivative with respect to the actual variables w and x, which is our downstream gradient. So dou f dou x is dou f dou a times dou a dou x, which is the chain rule, 1.648 times 0.2, which is 0.329, and 1.648 times 1, which is 1.648. And so with that, we've propagated all the way back and computed the gradient with respect to our inputs, right? And so that's how you build an expression tree or a computational graph for a set of expressions. And then you do your forward pass for your given set of inputs, and then do the backward pass using the chain rule to consistently evaluate the sensitivities or the local gradients at each node, take the upstream gradient, and then compute the downstream gradient and push it further down the set of nodes. So hopefully this is giving you a foundation, and you can now use this foundation to build an Autograd system, which we will do later. And a very good application of this is backpropagation in neural networks.